strong or weak, we don't mean it in the way that you probably think of something being strong, being dangerous, or being, um, well, dangerous, versus something that is weak. This is not true in the case of acids or bases. The strength of an acid and a base is determined by how it reacts in water. So I'm going to keep my analogy here of the bodybuilder versus the nerd. If you give both of these gentlemen a swirly, meaning you put their head in the toilet and give it a flush, the bodybuilder is going to lose a lot of self-esteem because he got beat up and he's a big guy. He's probably compensating for something. So putting his head in a toilet is bad enough, but if you flush it, he's going to go to pieces completely because he's never been treated that way before. However, the nerd, you flush his head in a toilet, he just calls this a Tuesday and is more or less unaffected. So he'll stay together. He keeps his composure, keeps his cool. In the cases of acids and bases, it's the same way. A strong acid, when placed in water, completely falls apart, can't handle it, breaks apart into its little ions. Whereas a weak acid, when placed in water, it doesn't care so much. Less than 1% of it will dissociate, will fall apart into its ions. So let's talk about who's the strong people and who are the weak people in the world of acids and bases. So your strong acids are all your hydrohalics. So hydrochloric acid, hydrobromic, hydroiodic, all the halogens with the exception of fluorine. Fluorine is not a strong acid. It doesn't go to the gym with the other ones. Because fluorine is too small. It can't make it past reception. You must be this big in shielding. You must be at least 2 valence shells thick to make it into the gym. So fluorine's not included. Another strong acid is nitric and sulfuric acid and phosphoric acid. And if you line them up that way, 1, 2, and 3 hydrogens. And each one of those have a different name, which we'll talk about later. Phosphoric acid, though, he's a sometimeser, so I'm not going to include him in the 6 that you must know. Instead, I'd rather you know that perchloric is always a strong acid. When I say that phosphoric is a sometimeser, it means that in your textbook it says phosphoric is a strong acid. However, the AP test, since that one depends on which book you get its strength from, will tell you differently. The AP test does not usually include it. So the 6 strong acids that you absolutely must know are all the hydrohalics, except for fluorine. Remember, he's the little guy. He's too small. He can't come and play. Nitric acid and perchloric acid are the 1 hydrogen ones. And sulfuric acid is the only diprotic acid, meaning it has 2 protons, 2 hydrogens it's willing to donate. And we'll go into that definition in just a few minutes. What are the strong bases? Well, remember your solubility. Any group 1 and most group 2 metals are soluble, and hydroxide is what gives us bases, according to Arrhenius. So group 1 and group 2 metals, hydroxides, are our strong bases, with the exception of magnesium and beryllium. So these are all the strong guys you need to know. If it's not in this list, guess what? It's weak. So everybody else falls into this category with the nerd. So the next time you push someone's head into a toilet and they start to cry, tell them it's okay. They're a strong acid because they're falling apart. But if they just shake it off, they're a weak one. Chances are most of us are weak acids. Who cares if your head goes in the toilet? Let's talk about what K means for both of these. A strong acid will dissociate completely, which means that if you put in 1 mole of hydrochloric acid, you're going to have 1 mole of hydrogen ions and 1 mole of chloride ions. So that means that your K value is going to be greater than 1 or greater. So for strong acids, your K values are hugely larger than 1. Because at equilibrium, K equals the concentration of products over reactants. And if the vast majority are dissociating, you're going to have the vast majority, the largest concentrations on the top of your, top of your fraction, and as you know from the previous unit, some will go back to being that compound hydrochloric acid, but it's a very, very small amount. So you're dividing by essentially something just greater than 0, like on the orders of 10 to the lot. So your value of K in the case of a strong acid is going to be absolutely huge. Whereas if you have a weak acid, holy crap, I have made the hugest error. Let's flip these so I don't look like an idiot. K is greater than 1. In the case of a weak acid, it's what I had before, where most of your reactants are staying. The concentration of your reactant is staying relatively the same, but only a few, less than 1%, are dissociating. So your value of K is going to be infinitesimally smaller than 1. Oh Lord, that was a math blunder if ever there was one. Now some of you might be wondering, why not hydrofluoric acid? Well, if you remember from your first semester chemistry or your first year chemistry, it all goes back to the size of the atom. The bond between hydrogen and fluorine is a very particular type of bond. It's extremely polar, and this has to do with the size of the fluoride ion. The strength of a bond is determined by how close two atoms are to one another, how close two nuclei are to one another. Fluoride is one of the smallest atoms on the periodic table. Fluorine is one of the smallest atoms on the periodic table. And when it forms the fluoride ion, it is still one of the smallest atoms. And therefore, since it is the smallest, its nucleus is not shielded as well. What do I mean by shield? If we look at a Bohr model of fluorine, we have 2 valence shells around it, like so. But if we compare that with chlorine, which would have 3 valence shells, or bromine, which would have 4 valence shells, you see that the radius of each one of these atoms is increasing. And if little old hydrogen wants to get in here and form a bond with them, hydrogen, in the case of fluorine, can get this close. In the case of chlorine, can get to there. And in the case of bromine, is way, way out here. Now, if the strength of a bond is determined by how close the 2 nuclei can be to one another, it's very obvious from if you look at the Bohr models that fluorine is the closest. So this is the strongest bond. And if we look at a table that has the bond strengths of each one of these compounds, we see that hydrofluoric acid has the highest bond energy. And therefore, the water molecules have a very hard time pulling this hydrogen away from fluoride. And therefore, it is a weak acid. However, since when the bond energy decreases, the acid becomes stronger. So hydrochloric acid is strong, and hydrobromic acid would be stronger than that because its bond energy is less. But that does not mean that hydrofluoric acid is in any way safe to handle or that it is not dangerous. If you have a drop of hydrofluoric acid on you, you most likely will have to have whatever limb the drop is on amputated, because hydrofluoric acid sucks the calcium literally out of your bones, and the only way to prevent further degradation of your skeletal system is to amputate the limb. Less than 2% or more on the body is automatically known as lethal. And that's why we don't play with it in lab. In talking about oxy acids, the reason that perchloric acid or hyperchloric acid is the strongest of all the acids you'll see is because it has the greatest number of oxygens. As you increase the number of oxygens, you increase the strength of the acid. And this deals with the electron density. It's kind of like increasing the number of horses pulling on a wagon. In this case, we only have 1 horse. In this case, we have 2, so that's pulling more and more electrons. It's becoming more, the electron density is increasing around this chlorine-oxygen bond, and that's pulling electrons from this oxygen-hydrogen bond. As I increase the electron density around these chlorine-oxygen bonds here, that pulls more and more electrons away from the oxygen-hydrogen bond. Between this chlorine and oxygen bond, there is a huge electron density, and that's pulling more and more electrons away. So the bond strength begins to decrease between the oxygen and hydrogen. As that bond strength decreases, it becomes easier and easier for water to come in and dissociate this compound. Another explanation deals with the oxidation state of the chloride ion, of the chlorine. As the oxidation state of chlorine increases, it becomes a stronger and stronger acid, because as the oxidation state increases, that makes chlorine more and more electronegative. As chlorine becomes more electronegative, it pulls electrons away from the oxygen-hydrogen bond. Either one of those explanations on AP exam will give you credit. So discussing electron density is the best method, but I believe that by discussing oxidation state, you can also earn some points. The stronger an acid, the weaker its conjugate base. What does that mean? Well, hydrochloric acid will dissociate completely. It's a strong acid. But as you know from the previous unit, that while this is a strong acid, will dissociate completely, this arrow is very, very heavily influencing towards the forward reaction. There is just a teensy bitty amount going in the reverse. An amount so small, we call it negligible. It's negligible, the amount of chlorines that are colliding with hydrogens and making hydrochloric acid, because as soon as they do, they're dissociating again into hydrogen and chloride ions. But they're still doing it, just a teeny bit. So while hydrochloric acid is a very strong acid, chloride ions are a very, very weak conjugate base, because very few of them are going to come back to make hydrochloric acid. And the inverse is true, meaning that if you have a strong base, it makes a weak conjugate acid. So there's a term that will constantly come up in your notes, and you may have figured it out by now, but you may not have. K, the equilibrium constant, naked K is just being lazy. When we were discussing thermochemistry, it was KQ. When we were discussing concentrations, it was Kc. When we were discussing pressures, it was Kp. Well, when we discuss acids, it must be Ka. And if we're discussing a base, well, that's Kb. Now in acids, as you saw from this diagram, the hydrogen is always attached to an oxygen, because the oxygen-hydrogen bond is the bond that breaks. So in a carbonic acid that has a carbonic group, COOH, it's the bond between this oxygen and hydrogen that break. And all carbonic acids are weak acids. Organic acids are weak acids, acids containing carbon, because they contain this carbonic group. Now, the vast majority of acids are weak. This means that equilibrium, when it is established, lies far to the left, meaning reactants are favored. The Ka is a representation of this. Since your reactants are favored, you have a larger denominator than you do a numerator, and therefore Ka is usually a lot less than 1 in the case of a weak acid. It is set up the same way as all the other Ks we ever did, reactants over products. Just always remember we exclude water from our K equations when you're asked to write Ka for an acid or a base. In the case of a weak base, the same can also be true, where Kb would be a lot less than 1 because reactants are favored, and they will produce very few hydroxide ions. But what if your acid, your weak acid, does not contain hydroxide? Where does the hydroxide come from then? Like in the case of ammonia. Ammonia, hopefully by now you know, is a base. Where does the hydroxide come from that makes ammonia basic? Well, ammonia is not by itself. it's in an aqueous solution, so that means water is present. What happens here is that nitrogen looks over at this hydrogen and is jealous and wants it. So it offers its 2 electrons and is like, hey baby, I can provide the same thing oxygen's given you, but you don't have to stay with that. So hydrogen goes, oh yes, I want some of that. So nitrogen provides both electrons to the bond with hydrogen, forming ammonium. And the bond between hydrogen and oxygen breaks, leaving a hydroxide ion. And a bond then forms between hydrogen and nitrogen nitrogen contributes both. When nitrogen does this, it's called a coordinate covalent bond, because one atom is providing all of the electrons in the bond.